Well, this evening, my colleague Chin and myself are going to speak about quantum cryptography. And it has been said that quantum crypto is probably the most advanced cryptographic scheme ever conceived. But as we'll show you tonight, it's not flawless, and we're going to report at least one flaw. Before I get more into the details, I would like to mention that this work actually is a joint collaboration involving 4 universities. The work was actually originated by the Norwegian Institute of Science and Technology, and later on it was joined by the National University of Singapore, the Royal Institute of Technology in Sweden, and the Polytechnical State University of St. Petersburg. For more details, you can visit the website of the Norwegian University. Here's a brief outline of the presentation. I will start by briefly reminding you about the general concepts behind quantum cryptography. Then I will present to you one general quantum hacking strategy, which is actually based on an intercept recent attack. And this attack is going to target the single photon detectors which are incorporated in our quantum crypto systems. And actually, most of the quantum crypto systems available on the market, they use avalanche photodiodes. So I'm going to discuss a bit how those avalanche photodiodes are working at the single photon level. And then I'm going to show you that, surprisingly, when those avalanche photodiodes are submitted to bright illumination, you can control them. And you can then hack the quantum crypto systems. Then Chin will take over, and he will present an attack on a real quantum crypto system together with the hardware demo. So you will see why we carried this 30 kilos box of equipment. And one thing about this real quantum crypto system is that it is built with a homemade single photon detectors. So later on, I'm going to discuss how you can actually hack commercial units. And hopefully there will be time for final remarks and questions. So first, a brief intro of the general concepts behind quantum cryptography, which is also known as quantum key distribution, or QKD. Since it's a hacking conference, I guess you know already the name of the usual suspects. So there is Alice, sender, Bob, receiver, and Eve in the middle playing the game of the eavesdropper. On that picture, you can see Eve writing letters on a piece of paper and throwing the piece of paper to Bob. And well, in quantum crypto, we don't use piece of paper. We use single particles of light, single photons. And we actually use one single photon per bit. And each bit of information can be encoded on a property of the single photon. It can be encoded on the phase, or in the case of the example discussed tonight, the bit can be encoded on the polarization of the single photon. For instance, if a photon is detected with an horizontal polarization, you can attribute to it the bit value 0. And if you detect the photon with vertical polarization, you can attribute the bit value 1. And there are several reasons to use only one single photon per bit. Obviously, you don't want to, because if you have two, there's one photon for Bob and one photon for Eve, the eavesdropper. That you don't want. Another reason is that when you work at the single photon level, you enter the realm of quantum mechanics. And then the security is granted by the laws of quantum mechanics. And you cannot break the laws. At least that's what you are told. And those laws bear several names. One you might have here is Heisenberg uncertainty principle. And in plain words, this principle states that observation causes perturbation. So if Eve tries to observe, to measure the state of the single photon, she will disturb this state, and this way Eve can be detected. Another way of looking at it is invoking what is called the no-cloning theorem. And basically, this no-cloning theorem states that in the quantum world, there is no perfect copy machine. You cannot copy an unknown quantum state. This is forbidden by quantum mechanics. An alternative way to look at it is under the view of complementarity. I've put pictures of Alice and Bob, and I mean, so musically speaking, you could say that Alice and Bob complement each other, but you wouldn't want Alice to sing one of Bob's songs. So, in a way, they complement each other, but they're also incompatible with each other. And complementarity exists in physics with several other variables, or we say several other observables. For instance, you might remember, if you study quantum mechanics, that you cannot measure simultaneously the position and the momentum of a particle. And that is believed to be a fundamental limitation of quantum mechanics. But here it is turned as an advantage to actually detect an eavesdropper. And well, let's go back to the case of quantum crypto here, where we have one single photon per bit and where the bit is encoded on the polarization. Here also, complementarity comes into play. And for instance, you cannot measure simultaneously the polarization of the photon in the horizontal vertical basis and in the diagonal basis rotated by 45 degrees. Those two bases are incompatible in the sense of complementarity. So for instance, if Eve catches a photon which has been encoded in the horizontal vertical basis, it's a piece of cake for Eve to measure the bit value. She just has to take, you see here, a polarizing beam splitter and two single photon detectors. And the polarizing beam splitter here will help to distinguish between horizontally and vertically polarized photons. Likewise, if the photon is sent in the diagonal basis, it's a piece of cake for Eve to measure the bit value. She just has to use a half-wave plate here, and this half-wave plate will rotate the polarization from diagonal to horizontal vertical. And then you just need to plug a polarizing beam splitter and two detectors, and you will be able to measure the bit value, either 0 and 1. But if you don't know in which basis the photon has been sent, then Eve is in trouble. And because of complementarity, she doesn't know which basis to choose. For instance, if the photon is sent in the diagonal basis, like here, and that Eve tries to measure the polarization state in the wrong basis, well, this state at the PBS will get random outcome, completely random outcome. So it can get no information in this case. And you might say that Bob will be in trouble because he doesn't know either in which state the photon is sent by Alice. He doesn't know if the photon is sent in the horizontal vertical basis or in the diagonal basis. But in the case of Bob, it's not really a problem, as we will see now. So here is a general QKD protocol as it is implemented. So in this case, Alice makes two random choices of basis. She randomly chooses bit value, 0 and 1, and she also chooses the basis in which she will send her photon, either horizontal, vertical, or diagonal. And Bob also makes a random choice of basis. He randomly chooses also the measurement basis. And this is illustrated on the previous slide here by this extra beam splitter, which randomly selects one basis or the other. And what happens then is that Alice and Bob, they can keep the bits for which they have used the same basis, because same basis means same bit value. And this can be done after the key exchange. I mean, Alice and Bob can call each other on a public channel and they can say, okay, for this bit, I have used this measurement basis. And then they keep all the bits for which they have used the same basis. On the other hand, if they have chooses different bases, they know that the results are not compatible and they can just discard the bits. Now, if Eve is in the middle, in 50% of the case, she will have to choose a basis. And in all cases, she will have to choose a basis. But in 15% of the case, she will choose the wrong basis. And in that case, she can be detected. Because later on, what Alice and Bob can do is that they can compare few bits for which they have used the same basis. So they know that all the bits should be identical. And if they find difference between the bits, then they will know that there is eavesdropping, and they can interrupt the communication. So it seems to be a perfect world. QKD has been proven unconditionally secure based on the laws of physics. And Eve seemingly has lost the battle against security proof. But there's a catch. There's a catch because those security proof, they're about as good as they can be. I mean, the quantum cryptosystems, they have components, and if you want to build security proof, you have to take models. You have to model the way the components behave. And of course, you have always non-idealities in components, and some of the non-idealities are taken into account into a proof. But as you know, the danger always comes from the unaccounted imperfections and non-idealities. And that's what Eve can actually exploit, the unaccounted imperfections of components, such as the single photon detectors. And that's the one we are going to address now. So yeah, it should be remembered that it's always a perfect world, but for hackers, and that's what this talk aims to illustrate. There's a very general attack to investigate the vulnerabilities of components such as single photon detectors. One such attack is what we call the fake state attack. Basically, it's an intercept resent attack, which is illustrated here. So you have Alice on the left here. You recognize now Bob's detection apparatus, and Eve is in the middle. And as you can see, Eve has a detection apparatus, which is an exact replica of Bob's. And with that detection apparatus, she intercepts and measures the quantum bits sent by Alice. For instance, on the example here, you can see that you got a click at the detector registering vertical polarization in the horizontal vertical basis. And then Eve has a fake state generator with which she sends a fake state which ideally should address the exact same detector at Bob's side, while keeping the three other detectors completely blind. So is it possible? Well, if you listen to quantum mechanics, the answer is no, because of the no-cloning theorem. But there are ways around. Let's do now an assumption. What if all those four detectors always click at intensity I0 and never click at intensity I0/2? Then, in the example here, where this detector clicks, corresponding to vertical polarization, Eve can send a fake state with vertical polarization and intensity I0 at this level. So here you have a beam of intensity I0 going, vertical polarization, so the beam is routed here, intensity I0, you get a click, fine. Here, vertical polarization is not transmitted, so you get no intensity here, no click. Now, in the second basis, your vertically polarized photon at the half-wave plate will be rotated to 45 degrees. And then at the PBS, the beam will be split evenly with half the intensity. And in our what-if scenario, those two detectors will not click. So under those assumptions, the quantum cryptosystem using these kinds of detectors are vulnerable. So the question is, are there many single photon detectors working according to our scenario? And the answer is a resounding yes. So let's discuss why. Nowadays, most of the quantum cryptosystems available, they use single photon avalanche diode, SPAD. And that's the one we have been targeting, and we're going to show now that currently none of them is really safe. And the reason basically has to do with the difference between ideal and real. Should always stick to reality. You have an illustration here of the clicks recorded by a detector as a function of the optical illumination at the detector. You see here that you have pretty low intensity level, below picowatts. And we are in the so-called Geiger mode, where we have single photon sensitivity. So you can see there that the detector's count rate increased linearly with the optical illumination, as you would expect from a detector. And ideally, you would like it to go this way up to higher intensity. But as you can see, below tens of picowatts, the count rate saturates and eventually goes down to exactly 0. So under bright illumination, the avalanche photodiode becomes completely blind to single photons. We can see that you can only start to control the detector just by using bright illumination. So how is that possible? Well, then you have to go into the working mode of the detector. And basically for avalanche photodiodes, you have two working modes, and it depends on the voltage that you apply at those diodes. Above a so-called breakdown voltage, in this regime, you are in the regime where you can detect single photon. Basically, the device operates as a trigger device. I mean, a photon arrives, it triggers an avalanche, and the gain is nearly infinite. You record a click. Below breakdown voltage, well, the diode behaves essentially as a mere linear amplifier. That means that the output of the detector is proportional to the light you input in. The gain in that case is much lower than 1000. So if you have just a single photon coming into the detector, this gain is not enough. And to make the detector click, you have no single photon sensitivity. So one question you can ask yourself is, would it be possible that bright illumination bring the SPAD to work from Geiger mode into linear mode, where there is no single photon sensitivity, because that would explain why the detector is blind? And if it's the case, a second question is, if you can bring the detector to work in this regime, is it still possible to make the detector click controllably? And the question, again, is yes. The answer is yes. So let me give an example in a case of a detector for which the avalanche is passively quenched. So what you can see here is the simplified circuit diagram of the detector. So you have the APD here. The APD is biased above breakdown voltage with this power supply. And whenever you have an avalanche, you have a stray capacitance here, which quickly discharge in the APD and into this resistor. And the current at the resistor here is converted into a voltage, which is measured by a comparator. If the voltage goes above the comparator threshold, you get a click. And so under single photon illumination, this is what you can monitor here is the voltage at the APD. So without avalanche, the APD is biased at a voltage of, in this case, above 200 volts. Then a photon comes in. So the capacitors discharge in the APD into the resistor. So there's a voltage increase at this resistor. So consequently, there's a voltage drop at the APD that you can see here. And here the APD goes below single photon sensitivity. So you see that the bias of the APD is lowered at the level or below breakdown voltage. And then we end up in linear mode here. So the avalanche is quenched. We are back in linear mode. The bias voltage is below breakdown voltage. And then the capacitors slowly recharge. In our case, it takes about 1 microsecond, after which the detector is available again to detect a single photon. But if now you apply CW bright illumination, what happened is that photons keep coming back, and each little avalanche resets the voltage below the single photon sensitivity threshold. So under bright illumination, the detector is kept in the linear regime, where it works as just a linear amplifier. So as we saw on the previous slide, it's completely blind to single photons. But you can still make it click controllably if you apply a classical pulse above the comparator threshold recording the clicks. And you have an illustration here. It's an oscillogram showing the detector output as a function of input illumination. We apply here about 50 microwatts power, so we are well above single photon levels. And as you can see, the detector is completely blind. There's absolutely no click. The detector works as a linear amplifier below breakdown voltage. No click, the detector is blind. Now, if we apply pulses of typically few milliwatts power, then the signal here goes above the threshold of the comparator, and you can see the detector clicking with unity probability and very low time jitter. So you have a very tight control of the detector. And this is the intensity I0 at which the detector clicks. And what this oscillogram doesn't show is that if instead you apply a pulse of intensity I0 divided by 2, your detector will be completely blind. So we get in the what-if scenario that I mentioned before. The detector always clicks at intensity I0, and if you apply half the intensity, the detector gets completely blind. So you have a case to launch the intercept recent attack, the fake state attack. And it is illustrated here. So so basically the general idea is that Eve will force her detection result onto Bob by first using a control generator, sending bright illumination into all detectors to blind them. So all 4 detectors are blind. And then we consider the case here where, again, the detector recording vertical polarization clicks. What Eve has to do to address this detector is to send a fake state generator with vertical polarization and 2 times the threshold intensity at which the detector clicks. So let's follow the path of this fake state. So this fake state is split in 2 at the beam splitter. So here we get a pulse of intensity I0 and vertical polarization. So the PBS will route the signal into this detector, which will click. There will be no intensity in this detector, it will remain blind. Now, in the second measurement basis, the pulse of intensity I0 and vertical polarization will be rotated by 45 degrees at the half-wave plate. And then at the PBS, it will be split in 2 parts of intensity I0 divided by 2. And at this intensity, as we saw before, the detector gets blind. Okay. So, question is, does it work in practice? Well, for that I will let Chin present the attack on a real quantum crypto system.
Thank you. So now I would like to present you a working eavesdropper we have built against the existing QKD system. So firstly, I would like to describe this QKD system under attack. This QKD system is built by National University of Singapore. In this QKD system, there is an EPR source which is located close to Alice, generates pairs of entangled photons. And for each entangled photon pair, one photon is sent directly to Alice, and another photon is sent to Bob by the transmission line. And to detect the photons, Alice and Bob both use the same detection unit. We have seen this before, the same detection unit. And EPR source, EPR stands for the first letter of Einstein, Polosky, and Rosen, who have found this funneling property of entanglement. So for entanglement photons, if one measure one photon here, he will automatically know the measurement result of another photon at another place. So that means the photon pair is in a well-defined state, but each photon is in an undefined state. And this equation can describe this property. So that means if one photon is in the vertical polarization state, the another photon is in horizontal polarization state for sure. And if you measure the photons in another basis, say if you measure in the diagonal basis, if one photon is in plus 45 degree and another photon is in minus 45 degree for sure. So one photon is always orthogonal to another photon. This is a property of entanglement photon pair. And this is a structure of the EPR source. So here, a blue light generates from a laser diode focused in a BBO crystal. And from here, one blue photon comes in and two red photons comes out. And through the single mode fiber, one photon sent to Alice and one photon sent to Bob. And here you can see the picture of the EPR source. And for Alice and Bob's detector, we have brought one detection unit which is really used in Bob, and you can see it later in the demo. And here on the picture, it shows the inside view of the detection unit. You can see on the picture that this is a 50-50 beam splitter, and followed by the two polarization beam splitter. And here is a half-weight plate, and there are 4 avalanche photodiodes kept in the housing. So again, this is a normal QKD system. To launch our attack, we cut the transmission line and insert our eve. And our eve contains a replica of Bob to receive the photons, and the rest is a fixed generator to control Bob. The fixed generator mainly contains 5 laser diodes. The first laser diode is aligned to the circular polarization state, which will keep all the 4 detectors of Bob blinded. And for the rest of the 4 laser diodes, each of them is aligned to a certain polarization state, which target 1 detector of Bob. And all the 5 channels combined together by 50-50 coupler and goes to Bob. So now, for example, if Eve receives a vertical click here, the output will trigger the corresponding channel of pulse generator, drives the corresponding laser diode to generate the optical pulse to make a single click at the target detector. This is very simple. This is just how we get the full control of Bob. But this scheme didn't work perfectly because the 4 detectors of Bob are not balanced. They have different blinding power. They have different breakdown voltage. So for this simple control diagram, we only get nearly 100%, but not 100% control efficiency. So if you can see this matrix, each column represents that if send a certain fixed state, which detector of Bob has got a click. So at the diagonal elements, they are not 100%. They are from 96% to 99%. And the more important thing is that there is an error that the other detector has got a click. This is not very good. And what we want is to increase the diagonal elements to 100% and eliminate the off-diagonal elements. So the solution is that to introduce the pre-pulse before the main pulse. The pre-pulse is aligned at the polarization state opposite to the main pulse. So this main pre-pulse will blind the other three detectors deeper and make them harder to get a click. So therefore, the target detector will be relatively easier to get a click. So by improve this control diagram, we get 100% in the diagonal and there's no off-diagonal elements. So of course, to implement these pre-pulses, we need another 4 laser dials. So we improve our final scheme. So finally, the fixed generator of Eve totally has 9 laser dials. So far we have done this experiment in lab. And then we want to do the experiment outdoor. We moved to the campus of National University of Singapore. We have found 4 buildings. We laid 290 meters of fiber through the 4 buildings. And at one end of the fiber, in the building of the Center of Quantum Technologies, we place our Alice. At another end, in the office of physical department, we place our Bob. And down there, the transmission line goes through the mechanical department. On the picture, you can see that Alice contains the EPR source, the blue light, and the detection unit. And the Bob contains the detection unit and the timestamp card. And by this, we have run the normal QKD experiment between Alice and Bob. We have do the communication between Alice and Bob, and we have recorded every experiment result. We have recorded every QKD parameters, such as key generation rates and quantum base error rates. And after that, we disconnect the fiber at a certain point. We insert our Eve at this point. And if you can see on this picture, in this use case, this black things with a blue label is another detection unit, which is the copy of Bob. And the rest of the suitcase is the fixed generator to get the control of Bob. And this yellow fiber comes from Alice, and this fiber goes to Bob. And then we have also done the QKD experiment. We have also done the communication between Alice and Bob with eavesdropper. So after the experiment, Eve has got her private key the same as Bob. And the more important is that we compare the QKD parameters. All the parameters are the same as before the attack. Alice and Bob didn't notice the existence of Eve, so we have done a successful attack. So if we see some experiment result of, if we do the precise check of the Eve clicks, so we have made a time cut of the clicks in Eve. This is a time period of about 10 milliseconds. Every blue dot represents a click at a certain detector at which time. So we compare it with clicks in Bob in the same time period. So for me, it looks this looks quite correlated. And if we superpose them together, and we can see that every blue dot is overlapped by the red dots. So that means every if yeah, I will say it later. Every click in if has launched a click in Bob. So some of you has already noticed that. So this is a good correlation. So some of you has already noticed that this few click in if but not in Bob. But this is not a problem because after the transmission, Bob will review the timing information, and he will reveal at which time he has received a click. So by this information, Eve can throw out the clicks she has failed to launch on Bob. So after all, Eve has still get the 100% information of the keys of Bob. So all the clicks in Bob is a subset of clicks in Eve. We have done several experimental runs. The longest run lasted over 8 minutes. In this 8 minutes, Eve has sent to Bob about 12 million bits, and most of them are successful launched a click in Bob. And if we compare the QKD parameter, the key generation rate is always kept at 25,000 per second. And the quantum bits error rate is kept at 6%, which is lower than the alarm limit. This is very important, and there's no noticeable change after Eve's interruption. So we can see that we have done the first implementation of an intercept reset attack on the realistic conditions. And thank you. And last thing is to compare the QKD parameter by plots. So you can see before and after attack, the key generation rates and the quantum bits error rates are both kept at the same level. So then I will do a short demo to show how to get a full control of a single channel in the real detection unit used for Bob. I will first need to blind this channel and then to launch a single click at this channel. So the whole setup is here. If you cannot see it clearly, you can see the picture of the setup here. So here is the circuit of the fixed generator, and here is the pulse generator to drive the laser diodes. And here, this is a real detection unit used for Bob. And the output of the channel is connected to this counter and is already connected to the computer. You can see the counts of the here. The counts shows how many photons the detector has received per second. So now you can see it is sensitive to the background light. So if I cover it with a black cover, so the count has been decreased. So now if I power on a certain laser diode to keep it blind, oops. So it's not sensitive to any light. Even if I remove this black cover, it's not sensitive to any background light. So then, when I introduce the optical pulse, this is 10,000 optical pulse per second. Oops, you can see the detector responds at the same count rate, and even if I increase the optical pulse to 20,000, it will change at the same count rate. So this is a small demo. So now we have this is for attack against the QKD system by the homemade detector. But what about the commercial detectors? Seba will continue to present this.
Okay, so yeah, what I would like to present, to finish with, is illustration of control with this time an actively quenched detector. So a detector for which the avalanche is quenched actively. And this is a commercial model which is manufactured by Perkin-Elmer. That's the mostly used commercial single photon detectors at those wavelengths, so working with QKD systems in the visible or in the infrared. Yes?
Actively quenched, what does it actually mean?
That means that when you have an avalanche, you need to quench the avalanche. You need to lower the bias voltage of the diode below breakdown to quench the avalanche. And it can be done passively, as you saw on the first detector, or it can be done actively, like with this detector with some electronics. And you can see here simplified circuit diagram of the detector. So we see it takes a bit of reverse engineering for those detectors. And well, maybe I can try to get there. So you can see the APD here. And on the right part, you have basically the comparator which senses the onset of the avalanche. And then you have the quenching circuit. Basically what the quenching circuit does is that after 14 nanoseconds, it connects the anode of the APD to plus 30 volts. So it quickly reduces the voltage difference at which the APD is biased. So it quenches this way actively the avalanche. And 20 nanoseconds later, there's also a reset circuit. So that's the quenching part of the circuit. And here you go into what you have here actually is the power supply which biases the APD at about 350 volts. To go back. Okay, and what Eve does in that case, again, the strategy is to blind the detector, to bring him to work from Geiger mode to linear mode in which the detector is blind to single photons. And in the previous case, you saw that Eve was using CW, bright illumination. In that case, what we use to control the detector is pulsed illumination. But basically, that's the only detector-dependent difference. So Eve applies here bright pulse, typically 50 nanosecond wide, above 2 milliwatt optical power, so much above single photon level. So, and here the current goes pretty much. And you have here a current limiting circuit, which kicks in when the current goes above 10 milliamps. And the current is drawn into this decoupling capacitor, C9. And here you have the output of an operational amplifier. And this operational amplifier is pretty slow, and the output is overloaded by the current here. So as a result, the operational amplifier outputs deeps, one typically few volt deeps signal onto this FET transistor. And this transistor actually controls the power supply which bias the APD here. And when the Eve sends bright pulses of frequency typically over 70 kilohertz, the power supply gets disrupted by the 1 volt deeps signal output by the operational amplifier. And usually the power supply phase locks to the frequency of the perturbation. And as you can see on the next picture, the detector gets under control. So what the picture shows actually here is the monitoring the bias voltage at the APD as a function of the frequency of the bright pulses that Eve is sending. So under normal operation, the bias voltage is around 350 volts. And as you can see, when Eve applies a pulse of increasing frequency, the bias voltage drops. And when it drops by more than 12, 14 volts, typically, the detector gets completely blind to a single photon. And that corresponds to the field squares and dots and so on. So here you have a regime where the detector gets under complete control under bright illumination. You can see on the right part of the figure that there's another region where you can control the detector. And surprisingly, the bias voltage is back to the nominal value. So you could say, hey, how can you control the detector here when the bias voltage is, again, around or above breakdown voltage? It should work again as in Geiger mode. And the assumed reason for that is the following. When you apply very bright illumination, you start to heat the APD chip. And one known feature of heating is that it will raise the breakdown voltage of the APD. Because before, you have a set breakdown voltage, and you bring the bias voltage below breakdown, and then the detector is blind. But under bright illumination, you can see that the bias voltage is back into nominal value. But what the heating produces is that it rises the breakdown voltage. So again, the diodes end up below breakdown, and you get it under control. What you see here is oscillograms of the detector output as a function of optical illumination. So here you have the bright pulses that Eve sends, and you can see that, of course, those bright pulses triggers a click at the detector, but between two clicks, the detector is completely blind. Now, if here you apply a pulse of sufficient intensity, then you get controllably the detector to click with unity probability and very low sub-nanosecond time jitter. So you get the detector under complete control again. And then we return to the fake state generator.
Quick question.
Yes?
Quick question about the heating effect. Have you devised any experiment to check whether that is actually heating or not? For example, walking very, very slowly through the various frequencies that you're showing. It struck me that the variable that in your plot seemed to be characteristic for the transition between regime 2 and 3 was really the
Hello?
pulse frequency and not the and not anything else.
Yeah, you're right. I mean, the question was whether we had assessed that this transition from one region to the other was actually caused by heating of the APD. And at this point, it's an assumption that we have to check. What we know is that a known cause of rising of the breakdown voltage is heating. And I mean, we thought that it could be an explanation, but that still needs to be checked. Okay, so we're back to the fake state generator, and basically what should be reminded in this presentation is that somehow what you need to control the crypto systems equipped with avalanche photodiode is a control generator to blind the detector. And as you can see, depending on the detector, sometimes you will blind it by using CW illumination, sometimes by using pulsed illumination. The idea is to bring the bias voltage of the APD below breakdown and to get the detector to work in the linear regime. And once the detector is in this regime, you get all detector blinded, then you address the target detector by a fake state with the right polarization and with an intensity above the threshold that will make the detector click. And that we have seen at half the intensity, the detector will remain blind. So one last question this presentation raised is whether QKD is practically secure or not. And some people will always say, well, yes, it's secure if you build it right. But you can only say that there's not really a way to build it right. You can only build a device to within certain tolerances. And some tolerances will come with unknown potential problems, such as the one we have reported here. So it's still early to say whether or not QKD is more secure than other cryptographic schemes, because QKD is also at an early stage. But what this study teaches us is that at this point, you don't need to break the laws of physics to break quantum cryptography. So I expect it's going to be a cat and mouse game for quite some time until we get a final answer to this question. And with that, we thank you for your attention and welcome questions. Thank you.